Across the globe, weather sensors are battered by wind and rain, logging atmospheric conditions every hour of every day. Each individual station captures thousands of distinct data points. When multiplied by thousands of locations worldwide, this generates a massive, never-ending stream of raw log data. This volume introduces an immediate engineering bottleneck. The continuous accumulation of logs quickly outpaces the memory and processing capacity of any single server trying to ingest it. Traditional single-threaded software architectures operate sequentially. If you force one machine to analyze this volume line by line, the computation eventually crashes under the weight of the queue. Effectively analyzing these phenomena requires a method for circumventing the physical processing limits inherent to individual hardware units. The solution to that hardware bottleneck is MapReduc, a programming model specifically designed for large-scale data processing. Its core utility is inherent parallelism. MapReduc divides a massive processing task and executes it across many different machines simultaneously. By distributing the load, a network of standard servers can perform calculations that would otherwise saturate the throughput of a single high-performance machine. However, MapReduc cannot parallelize every dataset. To allow for clean division, the raw data must possess a specific structural format. Distributed computing relies on rigid rules. The efficacy of the process depends on the underlying structure of the raw data being ingested. To see how this format dictates parallel processing, we look at the National Climatic Data Center dataset, our primary case study for MapReduc optimization. Before it hits a server rack, this data originates from physical weather sensor apparatuses, tracking actual, real-world meteorological elements in the field. Historically, analysts had to sift through these physical paper records by hand to isolate specific meteorological trends. Today, the NCDC generates vast digital logs that are semi-structured and strictly record-oriented. Translating real-world weather phenomena into these rigid, record-oriented digital files is the first step toward enabling distributed analytics. The NCDC uses a specific format to store this information, line-oriented ASCII. In this context, line-oriented means every single horizontal line of text represents one complete, independent data record. This single log line is densely packed with no standard delimiters. Variables rely instead on fixed-width character lengths. Temperature always occupies the same exact spaces. This consistency allows a program to target and extract just the temperature variable, ignoring all surrounding optional data. This rigid, predictable formatting means the processing machine only pulls exactly what it needs without having to interpret the entire line. Now, scale that single parsed line up. Imagine confronting a massive log file containing millions of these dense ASCII lines. Remember, because each record is line-oriented, no single line relies on data above or below it. This line-by-line independence allows massive files to be cleanly sliced into smaller chunks. The first chunk is isolated and routed to server node A. Simultaneously, a second chunk routes to node B. The remaining chunks distribute instantly across dozens of parallel servers. Structural independence at the atomic record level provides the mechanism for achieving scalability at the server level. Following that division, each machine holds a manageable fraction of the total dataset. Every node fires up the MapReduc program, simultaneously executing the exact same fixed-width extraction logic we examined earlier. Because the processing workload is divided laterally across a fleet of machines, the time required to extract the temperature data drops significantly. Once the extraction is complete, the program enters an aggregation phase. The targeted temperature variables from all those separate nodes are funneled back together into a final, clean output table. MapReduc bypasses the physical memory and processing limits of a single machine by transforming one massive task into thousands of parallel microtasks. From an engineering standpoint, a developer still has to write the logic for that extraction program. However, the developer doesn't have to manually route data over a network. Hadoop serves as the foundational framework, automatically managing the logistics of splitting files and assigning chunks to the nodes. Because Hadoop handles the architecture, developers can write their MapReduc logic in a variety of languages, including Java, Ruby, Python, or C++. The system treats them equally. The underlying parallelization functions identically across the network, regardless of which language is deployed. This means successful big data analysis relies heavily on understanding the formatting rules of the raw files, rather than mastering one specific programming language. MapReduc abstracts away the complexity of the hardware itself. It grants developers the freedom to interrogate massive datasets using the software tools they already know. We started with a continuous, overwhelming volume of real-world weather logs and tracked the mechanics of translating it into actionable data. Frameworks like Hadoop and MapReduc achieve massive scale because the NCDC dataset utilizes a semi-structured, line-oriented format that allows for perfect division. Connecting thousands of servers to a raw data stream is ineffective if the information lacks the structural alignment necessary to divide the workload. MapReduc proves that true scalability is determined by the physical structure of the data itself.